Good evening. So last class we have seen about necessary condition for convergence of uniform convergence. Correct. The sequence converges uniformly to F if something happens for this sequence there. Okay. So now we are going to discuss about some class of functions. Okay, C of x. That is, this is defined as set of all functions f. So this means we have to speak about x. So x is any metric space. Any metric space. Need not to be in C or R. Any metric space. Okay. So x is a metric space, and we have some class of functions with respect to this x. So that is collection of all f, where f is a function from x to c. So f is a complex valued function which is continuous and bounded. So set of all continuous bounded functions are there in this class. Okay, so we are going to discuss about this class of functions. Okay, so what is this? Set of all complex valued functions on a metric space X, which is continuous as well as bounded. Now, this boundedness can be dropped out. When it can be dropped out? If there is something more about this X. Okay, so see what happens to this set if X is compact. If X is a compact set, then what happens to C of X? X is compact, then function f is continuous function. So continuous function on a compact set. Okay, I mean continuous image of compact set is also compact. So it is in C. Okay, R2. Okay, so it is closed and bounded, so it is bounded always. Okay, so if X is compact, then the C of X can be set of all f from X to C such that f is continuous. That's all. Class of all continuous function. Okay, continuous function on X. Clear? Now we will define some norm in this. Okay, so whenever we define some set or class, we have to give the norm or metric so that we can do something more about this. We can speak something more about this set. Okay, fine. So let define norm as norm of f in this set as supremum over x in x f of x, mod f of x. Okay, supremum. Okay, so this norm is defined as supremum. That's all. Supremum among all the elements in this set. Okay, so what you have to do? This we have defined. So we have to prove that whether this is a norm or not. So prove that whether this is a norm or not. So how to prove? One is non-negativity, and the other first condition is non-negativity. Second condition is we have to prove the constant multiplication, and third is triangle inequality. Okay, these three things you have to prove. Non-negativity is obvious because here it is modulus, so it is always greater than or equal to 0. And supremum will be greater than or equal to 0. So this is greater than or equal to 0. And what is there? Equal to 0 if and only if the x itself is 0. The norm x is 0 if and only if this itself is 0. That means norm f is 0 if and only if supremum of this is 0. Supremum of this is 0 means this should be 0. That means function itself should be 0 function. So this is okay. This is true for everything. Constant multiplication, norm of alpha f, which is supremum of mod alpha f of x, which is nothing but supremum of mod alpha into mod f, which is mod alpha times norm. This is true. Triangle inequality, norm f plus g. If two functions are there, f plus g from this, f and g from this, then norm f plus g is by definition supremum of mod f plus g of x. Here you can use, we know triangle inequality in modulus, so we can use that is less than or equal to and supreme of a plus b, supreme of a plus supreme of b. Okay, so supreme of f of x plus supremum of g of x, so which is nothing but norm f plus norm g. Okay, triangle is true. So this is a norm. This is a norm. Okay, so we don't have any problem with that. Now, after defining norm, what you have to do? We have to speak about this set. So what type of set is this? Okay, yeah, we'll see that. Okay. After defining norm, so norm means what? It is with one function. So consider two functions f and g. F and g are two functions from c of x. Then norm of f minus g, what is this? We know that this is supremum of mod f minus g of x over x in x. Correct? This we can write it as d of f comma g, which is define this. Define d of f comma g as norm f minus g, which is this. Okay, that means what is that? We have to prove that this is a metric. D is a metric. Metric same thing. Metric also non-negativity. I have to prove that non-negativity triangle. So almost it is obvious from this. So that we can prove that. Okay. So this is an exercise. Similar to this, we can prove that. Okay. So check the condition, three conditions, and prove that D is a metric. Okay. So when you define some metric on this space, this becomes what? It is a metric space. Which C of x is a metric space. Metric space with metric as D. Okay. So this we can write it as C of x comma D is a metric space. Clear? Now, there is a result on this. It says that if there is a sequence of functions fn which is converging uniformly to some function f, this is nothing but, this is equivalent to say that if there is a sequence of functions which is converging pointwise to f with respect to d, this metric d. This metric means what? Metric on this space. Okay, so convergence of some sequence of functions with respect to this metric on this space is equivalent to say that convergence is uniform. That's it. We have to tell that convergence is uniform. How we can tell that? Use the definition. Definition of this. Fn converges to f with respect to d means what? For any epsilon greater than 0, there exists delta, there exists n in n such that d of fn comma f is less than epsilon for every n greater than or equal to n. This is by definition. This is equivalent to say that this all will be as it is. This will be d of fn comma f will be, what is the metric? Supremum over x in x mod fn of x minus f of x. This is less than epsilon for every n greater than or equal to n. And this is equivalent to say that supremum is always less than or equal to that element. So this is mod fn of x minus f of x is less than or equal to this, which is less than epsilon for every n greater than or equal to n. Correct? And what is this? this all will be there. Mod fn of x minus f of x is less than epsilon. This is true for any x in x. Okay, it's true for every n greater than or equal to m as well as any x in x. So this is definition of what? Convergence, uniform convergence. So this implies this is happens if and only if fn converges to f uniformly on x. That's all. So whenever we say that some sequence in this space converging, that is nothing but that convergence is uniform. Okay, so there is no pointwise convergence there. It will be always uniform convergence inside this space. Okay. Now, so we have what is this? We have a space C of x with a metric D on it. D of f comma g is norm f minus g, which is given by this metric. Okay, this we have. Now, we're going to tell you something about this norm there. Okay, so this particular norm, normoid of this g, this f. Okay, this particular norm, mod f of x, is called as uniform norm. Okay, this is called as uniform norm. There are many types of norm. One such norm is uniform norm or supremum norm, anything. Okay, so this is called as uniform norm. Okay, so here this metric, this norm is called as uniform norm inside this space. Okay, inside this C of x. Okay, so if you consider some A which is contained in C of x, subset of this, and if you consider closure of A, closure of any subset of C of x will be uniform closure. Will be always uniform closure. Okay. Similarly, A contained in C of x, and if A is closed, then that is called as uniformly closed. Okay. Uniform norm, and closure of any subset is uniform closure, and subset is said to be closed. That is nothing but uniformly closed. Okay. So this uniformity comes because of this result. Okay. And there is another result. The C of x is a, we have seen that C of x is a metric space. Okay. So moreover, this is a complete metric space. Complete metric space with respect to uniform norm. Uniform metric. Uniform norm means like this. Uniform metric means with respect to DV out. With respect to uniform metric, the C of x is complete metric space. Okay. So complete means what? What is the definition of complete metric space? Whenever we consider a Cauchy sequence inside that set, that should be converging. Okay. Every Cauchy sequence converges. That's all. So what you have to do? In this, take a sequence Fn is Cauchy. Cauchy in C of x. Consider this. Then we have to prove that this sequence converges. That's all. Okay. So Fn is a Cauchy sequence in C of x, and it should converge. That's all. So we will use this definition, Cauchy definition. So Fn is Cauchy means for any epsilon greater than 0, there exists n in n such that this is Cauchy in C of x with respect to this uniform metric. So this will be d of Fn comma Fm is less than epsilon for every Mn greater than or equal to. Correct. And what is this? This is similar to this. Put the definition of this d of Fn comma F, that is supremum of mod Fn of x minus f of Fn of x is less than epsilon x in x. Okay. And supremum is always greater than or equal to Fm of x minus f of x, Fn of x. Correct. This is true for every x in x. That's also there. So this is less than epsilon. It means what you have got? Mod Fm of x minus Fn of x is less than epsilon for every Mn greater than or equal to n and for every x in x. This is true. Fine. But now if you see this, what you have? We have a sequence Fn of x for x in x. So this is a sequence inside complex plane. So C is a complete metric space. Complex is a set of all complex numbers is a complete metric space. So inside the complex numbers, we have got a sequence which is Cauchy. Here we have got that this sequence is Cauchy. That means what? This sequence will converge. So this will converge to some function f. Okay, let it be if it converges to some f. Okay, and we know that if it converges, it will converge uniformly. That also we know. So it will, moreover, it will converge uniformly. Now my claim is complete means it should converge inside this itself. Okay, that means the thing we have to prove is f belongs to C of x. That's all I have to prove. Okay, so this convergence is uniform. Each of this element is a continuous function. Fn's are belongs to C of x. Each of this element are continuous. So and this convergence is uniform. So this function is also continuous function. Okay. So continuous is over. Only thing we have to prove is we don't know x is bounded or not. Okay. So only thing we have to prove is f is bounded. Okay. If f is bounded, then f belongs to C of x. That's all I have to prove. Okay. But what do you know about f? This Fn is converging, Fn of x is converging to f of x. Use that and okay. For any epsilon greater than 0, this is true. So let epsilon be 1, which is greater than 0. Then there exists n such that mod Fn of x minus f of x is less than 1 for any n greater than or equal to n. This is that. Okay. Now, this we have to eliminate. This is true for every n in n greater than or equal to n, correct? So in particular, this is true for this n also. Minus f of x is less than 1. This is that. Okay, and this is greater than or equal to. That means we can write it as mod f of x minus mod fn of x is less than 1. Correct. This all are true for every x in x. Okay. So mod f of x is less than 1 plus mod fn of x. Okay. And these elements are inside this. Okay, so that is obviously bounded. So this is less than or equal to 1 plus m. If you consider m as the bound for this, so this will be 1 plus m there. Okay. So here what we have got? Mod f of x is less than 1 plus m for any x in x. So this means that f is a bounded function. So f belongs to c of x. So whenever you consider a Cauchy sequence inside c of x, we have told that that sequence will converge always inside this c of x. So this is a complete matrix space. Okay. So this is all about your uniform convergence and continuity. Okay. Only this part is there. First part is we have proved the necessary condition, sufficient condition for uniform convergence by the use of continuity. And next we have proved, we have speak about this c of x, okay, class of continuous functions. Okay, that's all in this. So next we have to see about uniform convergence and differentiation as well as integration. Similarly, so here we have used continuity and proved all those things. There we will see about differentiation and integration. Okay, these two parts are remaining. Okay, so we will do that in next.